All right.
Yeah.
Proposition Book 3, 25. Given a segment of a circle to describe the complete circle of which it is a segment. All right. Let ABC be a segment. Not sure really how to define a segment if I don't know the circle it's coming from, but let's put that aside for a moment. There it is, ABC. Then we need to describe the complete circle to which that segment belongs, and presumably, hopefully, it's unique. Well, we have A and C, so obviously we're going to join them by a line. And bisect it at D. Now it says let D be drawn from the point D at right angles to AC. So B doesn't really exist yet. So we can draw a line at right angles. So we'll do that. I guess it could meet on either side, but then we reorient this diagram so that the segment is on this side. So I'll call that B. Draw a line BD at right angles to AC. The angle ABD so that's, maybe I'll do it in green. The angle ABD is greater or equal to or less than BAD. Suppose we're going to handle all three cases. So suppose ABD is greater than BAD. And on BA, let BAE be constructed equal to ABD. Okay, so maybe I need a bit more room, we'll see. So on BA, so on this line, at the point A, we're going to construct an angle equal to ABD, which is greater than BAD. I'm not sure why I switched to equal to. Yeah, okay. So right, so we know we can construct on any line any given angle, and this angle here, which is BAD, by hypothesis at the moment, it's less than ABD. So I'm going to construct BAE, which contains BAD and is greater, and let it be greater on this side so that the E comes out as shown. So that's a construction we can do. And let EC be joined. I guess E itself, I need to decide on the length. Let the angle BAE be constructed equal to the angle ABD. Let DB be drawn through to E. Okay, well that's like a little bit of a strange way to say it, but I can construct a line such that BA along that line has the given angle. So just let that line go out to E. I'll put E over here. I'm just going to change my mind about E in a moment. Okay, then I can extend the line DB out and then just make E, rename E to be the point where they meet. Okay, so that's E, and then I join EC. Let me write this. The BAB could be constructed equal to ABD such that E lies on the extension of DB. Okay. Since ABE equals BAE, EB equals EA. Right, that's proposition 1.6. Since AD equals DC, yes, it's bisected, and DE is common, yeah, etc., etc. I'll just skip the argument. We understand this. AE is equal to CE. Right, because they've got the same angles, and yeah. Okay, so AE and CE are equal. Obviously, we're going to try and argue that E is the center of this circle, right? But AE was proved to be equal to BE. Therefore, BE is also equal to CE. So we have all three of these equal. AE, EB equals EC. So the circle with center E has ABC as a segment. Okay, so implicitly the deal here is that if you have a segment and 3 points on it, I guess, then, and if they're all equidistant, well, yeah, I think there's maybe a bit of a missing, wait, let's see, it's referring to 3.9. I mean, we can use the fact that circles can't pass through each other more than once, right? If a point be taken within a circle and more than 2 equal straight lines fall from the point on the circle, the point taken is the center of the circle. Okay, yeah, that makes sense. So the segment by definition is part of a circle. If the center were not E, then we would reach a contradiction because we've got this point E and it's got 3 equal lines falling on this segment, therefore on the other circle, therefore E must be the center. Yeah. Okay, so that's quite satisfying. But that's only one of the cases, right?
All right.
It's manifest that the segment ABC is less than a semicircle because the center E happens to be outside it. Yeah, because that's because BAD is less than BAE. Yeah. Okay, even if the angle ABD be equal to the BAD, if ABD, so now we're going back to the 3 cases, if ABD equals BAD. So let's go back to our diagram. A, B, C, AC, D. So ABD, if that equals BAD, AD being equal to, oh I see, BD and DC. Why is that? AD is equal to DC because that's bisecting. AD is equal to BD because you have these two equal angles, right? So then it's equal to both of them. All lines D, so we just apply the same argument as before, but directly will be equal, etc. Right, so it's the same argument, but with D equal to E. So now let's go to the final case. If ABD is less than BAD, and if we construct on BA, so it's the same construction, we just get something inside now, an angle equal to ABD. So as follows. So there's A, there's C, we bisect it at D, we have B, we have AB, but now ABD is less than BAD, and so I'm going to construct this angle in here, E. So construct on BA an angle equal to ABD. So I think it's BAE that I want to be equal to ABD. We'll see in a moment. An angle equal to ABD, the center will fall on DB within the segment ABC. And ABC will be greater than a semicircle. And therefore not a segment, I guess. Not sure why that's a problem. I thought a segment was just a piece that was bounded by a line drawn inside a circle in the circumference. Did it have to be less than a semicircle? A segment of a circle is the figure contained by a straight line in a circumference of a circle.
Yeah.
Don't see why.
I guess there are two of them, right? If you do that, which one? When they say this, does not mean one
Yes.
of them.
Yeah, that's right. Huh. Okay. Segment ABC will clearly be greater than a semicircle.
Is that part of the? I mean, does that matter?
Yeah, I don't really understand
it
this
is.
part of the argument.
Yeah.
Therefore, given a segment of a circle, the complete circle has been described. this last part feels strange. Okay, so we can construct E, then we argue as before that EB equals EA equals EC. And then we can just appeal to proposition 9 again, right? We've got 3 straight lines, so we know E must be the center of the circle. So it's the same argument. So it's the same argument as before. I don't know, like, this is just like a comment, I think. I don't think it's actually part of the argument.
Yeah.
So as before.
It looks like the proof is done, right? Because the picture is essentially just an obtuse version of the case 1. Right?
Yeah, that's right.
Yeah.
Yep. Okay, so we're done.
Cool. Thanks, Dan. I think we have probably enough time to do one more.
Yep.
Longer than usual. We're getting to longer.
Yeah,
things.
right.
So Dan, you have a paper version of Euclid, is that right?
Yeah, I do. Yeah, it's the
Yeah, I'm hearing you flip the pages. I'm like, huh.
Yeah, I find it more pleasant.
Somewhat difficult for me to do so because if I navigate out of roadblocks to look at Euclid, I mean, my laptop is not with me right now, and I guess I have my phone, but then it's super tiny.
Yeah.
Okay, so I should move over one more. So we have both boards. One more. There we go. Okay. So the next proposition is 26. 26, and probably this is all we have time for today. Okay. So this is the statement of the proposition was slightly confusing, so I'll rephrase it a little bit. Hopefully, I've rephrased it correctly. In equal circles, equal angles at the circumference and center stand upon equal circumference. So we're using circumference in 2 different meanings here. I guess it's not 2 different meanings. I mean, when I think of the circumference, I'm thinking of like the entirety of the circumference, but I think here is also used to refer to parts of the circumference of the circle. I don't know why. I guess segment is really the area that's bounded by the circumference and the line, right? So this is really just talking about I guess what we will say, we will call it an arc, I guess, right? So the statement of the proposition has maybe a superfluous hypothesis, right? So like we proved in the previous proposition, I forgot the number, 24, that the angle at the center is double the angle at the circumference if you're talking about the same circumference. So really it's superfluous, but I think in the proof they assume both. So I'm going to keep that and just make a comment here. You only need one. The other follows from if you have equal angles and circumference. Right. So I'm going to draw the circles. 2 circles. I don't know why I don't need 2 circles, but I guess I'll draw 2 circles. So these 2 circles are going to be what am I saying? Well, they're equal circles. So we're given 2 circles that are possibly distinct, but they're equal in the radii. And
this is it's a very strange way of stating whatever the hell it's trying to say.
Yeah. Right. But I'm going to copy it, right? So, so these are equal circles, and I have a part of the circumference. I'm going to call this B. Oh, I did it again. I have to BC, and the circle will have center G, and then H, and this is EF. Right. So have equal centers or equal angle. I mean, I'll mark in what is equal in a bit. So the claim is that draw these in. So there's a center, angle is center, angle is the circumference, and the claim is that these 2 are equal, and these two are equal. So the two blue, probably erase it. The two green marked angles are equal, and two red marked angles are equal. And so the claim is that if the marked angles are equal, then this part here, which I'll call BC, and this part here, this we'll call EF, these are equal. And so what I'll do, one more construction is I'll join up these two as well. Always join up the points you draw on the page. So that's the construction. Proof on the next page. Okay, so there's assume the circles, I guess with centers G, did I choose G and H are equal? Right, i.e. they have equal radii. They have equal radii. Okay, so what can we conclude from this? Well, if the radii are equal, we have a bunch of lines which are equal, right? So the radii here are, well, BG is a radius, GC is a radius, EH is a radius, and HF is a radius, right? These are all equal lengths because they are radii of equal circles. So what do we say? BG is equal to GC. Well, actually, I don't want to say it like that. I want, GC, they're all equal. GC equals EH equals HF, right? So they're all equal. Let me see. Okay. And so what we also have is by hypothesis, the green angle in the middle, they're also equal, right? So that would be BGC and EHF are equal. Okay, so you can already see that we've identified two triangles that are the same, equal, congruent, right? So by proposition 1.4, so way back to book 1, we have these two equal triangles because you have two sides and the included angle are the same. Then we can conclude that the base of these triangles are also the same. So at the base of triangles BGC and EHF bases of these two triangles are equal, i.e. one of the bases is BC equals EF. Okay, so we've concluded that, going back to the diagram, that is the base of these are equal, so I just mark them in, these are the same. And we're going to use proposition, I guess, one of the last ones, I don't know if I label this. Yeah, so the base of these are equal. So now the angle, this is the other assumption that we made, the angles BAC, this is the red marked angles, BAC and EDF are equal, right? And what do we know about this? Those segments, the segments BAC and EDF are similar, right? This is a definition of the segments being similar. So,
Right. I mean, you're making the statement where if both of these statements are true, then something. Oh, I see.
Yeah. They assume both. You're right. Even though you don't need to.
I think what Euclid is saying is if either one is true. Now, of course, they imply each other, so it's kind of like superfluous in the way you're saying. Yeah.
I thought that too, but they use both hypotheses, right? Because now I'm using the fact that those two angles.
Well, yeah, we just appeal. It's proposition 20 that you're mentioning, right?
Basically, that's where it's coming from, right? So, i.e., the segments BAC, the same labels, right? But now we're talking about the segments are similar, right? And similar segments on equal basis, right? We've shown that BC and EF are the basis of these segments, So similar segments on equal bases. So the bases are B, C, and E, F, right? We're showing them to be equal with the congruent triangle argument. So they're equal. So the segments are equal. So BC is equal to EF. So really, the proposition. Dan, can you remind me what the number is for the proposition? This is 24, right?
Similar segments of circles on equal straight lines are equal to one another. Yeah.
Yeah, 24. Right. So this is 24. And but the segment we're talking about is BAC and EDF. So that's like in the diagram, that's the bigger bit. But we are making a conclusion about the smaller arc, right? But the circles are equal, so we're subtracting the bigger arc from the circumference, and we're getting left with the smaller arc. So BC and EF, like those two circumferences, are then equal. So I'll just say that bit, right? So that's it. That's it for the proof. So really, it's an application of proposition 24.
Yeah.
And
yeah, I never quite know. Like, I feel like I would have not been surprised if this whole statement fell under Euclid's just general notion of equal or something, right? Like, you've got two diagrams that are equal, you just apply them to one another, the things are the same, right? You don't.
Yeah, I thought that too. I was going to apply them to one another because, BG, like the BGC and EHF, you can just move them on top of each other, right?
Yeah.
But maybe the notion of applying a circle on another hasn't really been talked about. We've applied straight line figures on each other. We just smack them on top of each other, and that's fine, right? Yeah, maybe he was hesitant to apply circles to each other. I don't know.
Yeah, it's interesting.
Yeah.
Some of these corner things are kind of the most interesting things about reading through Euclid. Yeah, cool. Thanks.
Yeah,
okay.
So actually, I don't know if maybe one more comment here.
Yeah.
Maybe not this one. I was like, if this no, it's the next proposition that I was looking at. I'll save that till next time.
Okay. Very good. Thanks, Ken.
Then see you next time.